Okay, so we are already at the fourth talk of the session. The title is Ruffle, Rapid Three-Party Shuffle Protocols, and Nishat is giving the talk. The stage is yours.
Thank you. Hello, everyone. So I'm Nishat, and I'll be talking about our work Ruffle, Rapid Three-Party Shuffle Protocols. This is a joint work with Pranav Sriram from JP Morgan Chase Bangalore and other folks at Indian Institute of Science that include Varsha, Arpita, Bhavish, and Soumya. So shuffle is the technique of rearranging elements in an ordered set. But what does this mean in the privacy-preserving context? So let's say we have an array of secret elements from A to Z, and this array is secret shared amongst a set of three parties. Now, secret sharing is a technique which allows you to split a secret, or let's say a color, into multiple components such that each of these components or each of these individual colors does not leak any information about the original secret or the original color. But when these components or the colors are mixed together, it gives you back your original secret or your original color. So we'll use this box notation around an element to denote that this element is secret shared amongst a set of parties. So given a secret array, if we had to apply a permutation on the elements of this array, it would result in rearranging these elements. So in this case, consider the permutation as displayed. This would result in rearranging the elements of your input array such that in the output array, the first element would be the third element of your input, the second is the 26th element of your input, and so on. And we want to replicate the same effect even in the secret shared domain. So essentially, we want to be able to apply a permutation on the secret shared elements of the array such that this results in rearranging the elements. And in the process, we also want to hide the permutation that is used for this rearrangement. This is what we term as the secure shuffle operation. So in summary, secure shuffle allows you to permute the elements of an array while ensuring that the elements as well as the permutation that is used for rearrangement remains hidden. And shuffle finds use in various applications such as ORAM, secure sorting, anonymous broadcast, to name a few. And anonymous broadcast is one such application which can be directly built on top of shuffle. So in an anonymous broadcast system, there are a set of N clients, each of which has a message, and they want to broadcast these messages amongst themselves such that after the broadcast, based on a received message, one should not be able to tell where the message originated from or who is the sender of the message. One way of achieving this is for the parties to send their messages to a central entity, and the central entity will shuffle the received messages and broadcast these messages back to them. While this ensures that the parties will not be able to tell who is the sender of a particular message, all the messages as well as the senders of the messages are known to this central entity. So to protect privacy of the messages and the senders of the messages against the central entity as well, the central entity can be replaced by performing a secure shuffle operation. And as I discussed, in a secure shuffle operation, your messages as well as the permutation that is used for shuffling will remain hidden, and thus this will allow you to attain the guarantee of an anonymous broadcast system. So our contribution lies in designing a secure three-party shuffle protocol called Ruffle via the technique of MPC, or secure multi-party computation. And in the process, we are able to tolerate at most one malicious corruption amongst the set of three parties. So as was discussed in some of the previous talks, MPC is a technique that allows a set of parties with private inputs to compute a joint function on the inputs while ensuring that at the end of the computation, all parties obtain the correct function output and nothing beyond the function output is leaked. And MPC also guarantees security in the presence of adversarial behavior by some of the participants. So we design a three-party honest majority protocol called Ruffle, and we aim to provide the strongest security of guaranteed output delivery, which ensures that no matter how the adversary misbehaves, at the end of the computation, all honest parties are guaranteed to obtain the output. And we also work towards attaining a fast response time, which is the time taken from the submission of the input to obtaining the output. And to aid in this, our protocols are cast in the pre-processing paradigm, wherein all input independent computations are moved to a pre-processing phase to pave way for a fast online phase. Now, in comparison to the prior works, we are able to uplift the security to guaranteed output delivery. And as far as the online complexity of the protocols goes, most of the protocols are designed to first perform a semi-honest shuffle operation, followed by a verification phase to verify the correctness of the computation. And we are able to improve the round complexity as well as the communication. In fact, the verification phase is designed such that the cost for the same can get amortized in the presence of multiple shuffle instances. So to understand, to give you an idea of where the improvements stem from, I'll give a quick overview of the Ruffle protocol. So let's say T is the array that is required to be shuffled. So T is going to be secret shared amongst a set of 3 parties. And for secret sharing, the following is done. So T is split into 2 components, where the alpha denotes a mask value, which is chosen independent of your input. And once the input is available, we are going to XOR the input with the mask and generate a masked value. Now, the mask is going to be 2 out of 3 replicated shared amongst a set of 3 parties. And note that this can be done in the pre-processing phase because the mask is going to be independent of your input. And once the input is available in the online phase, the masked value can be computed, and the masked value is given on clear to all the parties. So this is how the secret array T is going to be shared amongst a set of parties. Now, to ensure that the permutation that is used for shuffling also remains hidden in the process, the permutation is defined to be a composition of 3 permutations, and every party is going to miss 1 distinct permutation out of the 3, which ensures that the permutation pi will not be known on clear to any of these parties. And now our goal is to generate shares of pi of T, which is the elements in T rearranged under this permutation pi. So this is nothing but pi applied on the beta XORed with the alpha component. And we can now distribute pi on the beta and the alpha component. And if you notice, alpha as well as pi is independent of your input, and thus shares of pi of alpha T can be generated in the pre-processing phase. And once the input is available in the online phase, you can generate shares of pi of beta T. And because beta T is available on clear to all the parties, we leverage this fact to design an efficient online phase. Now, while this works while Ruffle is designed to handle the case of a standalone shuffle instance, we also identify the need to handle scenarios where multiple shuffle invocations are required, and these shuffles are required to be performed in a sequential manner. What do I mean by this? So if you recall the anonymous broadcast application, it is a perennially running system wherein you have to perform sequential shuffle operations. So let's say you have a set of n clients, you shuffle their messages, then there'll be another set of n clients, so you again shuffle their messages, and so on. So we identify scenarios where such repetitive sequential shuffle invocations are required and design protocols that are tailor-made to such scenarios. So specifically, we consider 2 scenarios that we term as independent shuffles and composed shuffles. In the independent shuffle scenario, let's say we have to perform m shuffles sequentially. These shuffle invocations are going to be independent of each other. And this is what happens in the example of anonymous broadcasts that I discussed. In the composed shuffle scenario, there is some sort of a composition of shuffles that is applied on your input. For instance, you perform your first shuffle invocation. Now, in the second invocation, the second permutation is going to be applied on the output of your first shuffle invocation. So at the end of m shuffle invocations, it's a composition of m permutations that you're applying on your original input. And such a scenario arises when using the graph-C paradigm for secure computation on graphs. So to cater to these 2 scenarios, we design Ruffle 1 and Ruffle 2 that build on top of Ruffle. And while the online phase of both these protocols is similar, and it requires performing M shuffle invocation sequentially, it is in the pre-processing phase where we are able to generate the required pre-processing data for the M sequential shuffles in parallel. And the way Ruffle 1 and Ruffle 2 differ is that Ruffle 1 is designed to leverage the independence of the shuffles in the independent shuffle scenario and use that to attain a pre-processing phase where the pre-processing data for the M shuffle instances can be generated in parallel. But when Ruffle 1 is used for the composed shuffle scenario, it breaks down and it requires the pre-processing also to be performed sequentially. This is where Ruffle 2 comes in to break this dependency present in Ruffle 1 for composed shuffles, and it allows you to perform the pre-processing for the case of composed shuffles also in parallel for the M shuffle instances. And because composed shuffles is a generic scenario and it subsumes independent shuffles, Ruffle 2 can also be used for independent shuffles. But because Ruffle 2 is designed for the more generic scenario of composed shuffles, it has a slightly higher complexity than that of Ruffle 1. Hence, Ruffle 1 is apt for independent shuffles, while Ruffle 2 is apt for composed shuffles. And in comparison to prior works, we observe that both Ruffle 1 and Ruffle 2 outperform the existing work in their respective settings, not only in the online time, but also in terms of the total runtime. Finally, we showcase the use of Ruffle 1 for independent shuffles for the application of anonymous broadcast and observe that we are able to uplift the security guarantee as well as observe improvements in response time. Similarly, we use Ruffle 2 for the application of breadth-first search computation via graph-C paradigm, and here as well we are able to see improvements in response time. So to conclude, we have designed a three-party honest majority shuffle protocol called Ruffle, which improves in terms of the security as well as the online round and communication complexity in comparison to prior work. And building on top of Ruffle to handle the case of multiple sequential shuffle invocations, we designed Ruffle 1 and Ruffle 2, which are tailor-made for the cases of independent shuffles and composed shuffles respectively. And we showcase the use of Ruffle 1 for anonymous broadcast and Ruffle 2 for BFS computation via graph-C. So you can find more details of the protocol in the paper. Thank you.
Yeah, thank you very much. Actually, two questions have been posted to Sulip, which by coincidence are actually aiming for the same question. So I would just consider these as one question. Namely, the question is, I'm reading out the first one. It looks like the technique can be applied to any number of parties greater or equal to 2. Actually, no, greater than 2, I would say. Is this the case? If yes, why did you focus on the 3-party setting?
Right. I think the technique can be extended to multiple parties, but the thing to note is that as you increase the number of parties, if you simply directly adapt this technique, it may result in increasing the number of rounds of the protocol. Right now, it requires just 2 rounds in the online phase for performing the shuffle invocation. So I think if you extend it to, let's say, the n-party scenario, you may end up requiring n number of rounds as well.
Okay. Well, thanks. Any other questions? There's one question at the very... Maybe in the meantime, maybe you can already set up your system.
Thanks for your talk. Did you mention that you get a guaranteed output delivery?
Yes.
How do you achieve that?
So essentially, we ensure that every message that is communicated is sent by 2 parties so that we can identify whenever there is a misbehavior, we can detect it. And we identify a conflicting pair of parties. And once we know that we have identified a conflicting pair of parties, we are guaranteed that one of the parties in this set is corrupt. And we rely on the residual party outside this conflict pair to carry out the rest of the computation.
I see. Did you have a chance to see what's the overhead of this operation?
Of
checking about the third party that's malicious, if it's malicious.
No, that part is not covered, right?
Right, thank you.
Thank you.
Okay, then I would say thanks again for the nice talk.